Hello and welcome back. In this video we'll be looking at one of the uses of the antiderivative, that being finding area. So when we take the derivative of a function, we normally think of that as the slope of the function. And when we take the antiderivative, we need to be sort of going backwards. If we're given the slope, we can find the original function. But if we're just given a function and we take the antiderivative, does it have a meaning? And it does. But I do want to put this in quotations because it's not exactly the area. And I'll be a little bit more specific in a little bit. But we'll do some examples first, and I'll show you why we can think of it as the area, and then what kind of goes wrong. So when we take the antiderivative, sometimes you'll hear it referred to as the integral. And so the antiderivative looks like this. And if you take a function and we know what its derivative is, when we take the antiderivative, we get back the original function. But there's going to be this constant here. And again, let me recap, why is there a constant here? If I take the derivative of this guy on the right-hand side, well, the derivative of f of x, of capital F of x, is little f of x, so I get what I want. And the derivative of c is 0. So the derivative of this whole thing is little f of x, and it doesn't matter what c is. So we always have to leave this constant in there because we don't know what exactly it is. However, we can change the notation here slightly. Rather than just having this symbol, this integral sign out front, we can put the integral sign out there with a and b, and a and b are called bounds. So these are called the bounds of the integral, and by putting those bounds there, it becomes what is called an integral, or you also hear this referred to as a definite integral. And this again has a very specific meaning based on what the antiderivative is. And this is, we find the antiderivative, and we plug in b, and then we find the antiderivative, and we plug in a, and subtract them. This is maybe a little bit bizarre. Why on earth are we doing this? But before I get into that, I want to show you one more notation for this. If you take the antiderivative, we will sometimes put a line here and put what our bounds are. And this means plug in b, plug in a, and subtract them. So this right here is quite a useful notation. It's quite compact. So let's go through an example, and I'll draw a picture of why this is the area. What on earth are we doing? So we have the definite integral now from 0 to 2 of x. So what we do using our formula, we find the antiderivative of x. So from last time, if we want to take the antiderivative of a function, we raise it to the 1 higher power, so 1 more than 1 is 2, and we divide by that power. So this is the antiderivative of x, and so far I haven't included my bounds anywhere. So what I'll do is I will include the bounds by doing the following. We draw this straight vertical line, kind of like half of an absolute value symbol, and we'll write 0 on the bottom and 2 on the top, and these are our bounds. And then what this means is that I plug in 2, and I plug in 0, and we simplify. So let me do this on the next line. So 2 squared is 4, times a half is 2. 0 squared is 0, times a half is still 0. So this whole thing is equal to 2. So there's a couple of points I want to address. I said that this was like the area, right? Well, where is the area in here? What is going on? So if I draw the function x, it's just a straight line going diagonally up. And it's going 1 up and 1 over. So where's the area here? Well, I'm going from 0 to 2. So if here's 0 and here's 2, and I look at the area beneath the curve. What's the area of this triangle? Well, the base length is 2, the height is 2, and the area of a triangle is going to be 1/2 base times height. So that's 1/2, 2 times 2. 1/2 times 2 is 1, times 2 is 2. So we get the same thing in both scenarios. The area, what's called the area beneath the curve, or the area between the curve and the x-axis, that is going to be our integral. This is what I mean when I say that the integral represents an area. The other thing I want to address is when I took the antiderivative, I didn't include the c here, did I? I just took 1/2 x squared. Where's the c? Where did that go? Well, let me show you what happens if I do include the c. So let's start over, and I say I take 1/2 x squared plus c, and I plug in 0 and 2. Well, then I have 1/2 x squared, 1/2 2 squared plus c. I'm going to take all that and I'm going to subtract 1/2 0 squared plus c. And what you'll see is that I have the 1/2 2 squared and the 1/2 0 squared, just like I had before. I also have a plus c and minus c. So guess what? Those constants cancel out. It doesn't matter what c is. I'm always going to be adding c and then subtracting c. So ultimately, I get the same thing, and it didn't even matter what c was. So when we're taking a definite integral and we're plugging in our bounds, don't worry about c. They'll cancel out anyway. So that's one nice thing about taking a definite integral as opposed to an indefinite integral. We don't have to remember our plus c. Let's do another one. So here we've got the same bounds. We're going from 0 to 2, but now we're looking at x squared. So if I draw a picture of what this kind of looks like, let's just draw a bigger picture. X squared kind of looks like a parabola. And from 0 to let's say 2, we've got this shape that kind of looks like a triangle, but it's not a straight line up here. It's a curved line. So the question is, what is that area? Well, I don't have a formula for that. I can't find this area just by using a formula for the area of something that looks like a triangle. I have to do my integral. So let's do that. I first take the antiderivative of what's inside. So I take the antiderivative of x squared. I take x raised to the 1 higher power, and I divide by that power, and I plug in my bounds, 0 and 2. The same as last time, but I think we'll get a slightly different answer. So here, 1/2 x cubed. If I plug in 2, I'll get 1/2 2 cubed, and I'll subtract 1/2 0 cubed. Again, 2 cubed is 8, times 1/2 is 4, minus, well, that's just going to be 0. So here, it's going to be 0. Or sorry, here the area is going to be 4. I think x squared is going to be a lot higher, so up here at 2, this is going to be at 4. So our triangle is going to be a lot more stretched out vertically, or shouldn't even call this a triangle. It looks like a triangle, but the top line is pretty curved. This is how we are going to find area quite often. So let's do one more example. And again, this is a function that I am not really going to be able to come up with a formula for. So e to the 2x is going to look something like this. It's an exponential function, so it's going to start growing and growing and growing. But as we get closer and closer to negative infinity, as we go off to the left, it's going to flatten out. So here I want the integral from -1 to 3. So maybe there's -1, and then over here is 3. So what we're doing is we want the area, use a different color so it stands out. So we want the area, and this thing, again, it kind of looks like a triangle, but not really. It's a curved line on top. I don't have a formula for this, so if I want to find this area, I'm going to have to take this derivative, or this integral. So again, e to the 2x, e to a number times x is quite a nice derivative to take. E to the something times x, we always get it as a as an antiderivative divided by that number right there. And again, I need to just plug in my bounds. And here, I'm going to take 1/2. So this is going to be e to the 2 times 3 minus 1/2 e to the 2 times -1. So if I pull out that 1/2, I've got e to the 6th power minus e to the -2 power. And this is something that I would need a calculator in order to solve. This is going to be the area underneath this curve here, but there isn't a whole lot more to it. When we're taking an integral, we take the antiderivative and plug in our bounds. This, if I take a second to just sort of recap, this is probably the most important thing that we'll do in these last couple weeks of the semester. The derivative is very, very important, as is the integral. And the integral is what we'll be looking at, how to solve lots of complicated integrals in the next couple weeks. But I will look more at this in the next video.